Hi, welcome to Chapter 2. We're going to talk about matter, what it is, because this matters, and the states of matter, because these states of matter absolutely matter. Ha, I couldn't resist. Okay, so that's the big question. I'm talking about matter because I said it matters over and over, I know, right? But what is it? What is matter? What is it? Well, matter is anything that has mass and occupies space. Maybe we should define those words, so you should write this down. Mass. Typically, we can think of mass as weight. It's really not exactly the same thing at all because weight has to do with gravity, but we're gonna let it go and just kind of think of it as weight. For our purposes, we can think of it as being the same thing. Occupies space. Well, I occupy quite a bit of space, and other people occupy a lot less space, and some people occupy, I've seen those Walmart pictures. OMG, they occupy a lot of space. Anyway, space. Usually our technical word for that is volume, which means occupy space, yeah. And all matter is composed of tiny little particles called atoms. Atoms, that's right. All matter is composed of atoms, which is why you should never, ever, ever trust an atom, because they make up everything. I know if I could do a soundtrack with laughter right here, I would do it because it's really freaking hilarious. Okay, well, here's a picture of an object containing all atoms. See, all these little balls, and we're gonna visualize atoms as being little balls. That's how we're going to visualize atoms for a very long time, little balls. In fact, most of the great scientists of the world viewed atoms as being little balls. And, you know, it's a pretty useful image, even though you should probably know atoms don't look anything like little balls, but we'll get to that another time. It's a good visualization. One of the first things we need to do in this class is to work up some definition words, because in order to be able to understand chemistry, you kind of got to speak chemistrian. And so in order to speak chemistrian, there's certain things you need to know. For instance, what is an element? Well, an element contains only one type of atom. That's it, just one type of atom. So here I have a picture of gold. Gold contains only gold atoms. By the way, the symbol for gold is AU. That is one of the things you do need to know. Gold has AU as its symbol, and it's only made up of identical little balls, one type of atom. Now here's a mind blower. A molecule can be an element. Whoa. Okay, so look, we got the word molecule. See the word molecule? Molecule means these little balls are bonded together, hooked up together, fused together, chemically connected. And yet this molecule is an element. And the reason it is it's only made up of one type of atom. So some great scientists will come along in your reading and say elemental hydrogen. Hydrogen, yeah. An elemental hydrogen looks like that. It's made up of two little balls of hydrogen. So that's why it's an elemental, because it's one type of atom. And we would write its formula as H2, the two representing the two little balls. Elements that are made up of tiny little balls are called, well, two tiny little balls are called diatomic. The prefix di means two. Typically, my rule for taking notes is if I write it down, y'all need to be writing it down as well. It's helpful. So here we have two diatomic atoms. It just simply makes it a noun. So this is a thing that is made up of two atoms. So take a look at that. That's nitrogen. We would write nitrogen as N2. And it's an element. It's called an elemental molecule. Even though they're bonded together, it's still an element because they made up of the same little balls. Here we have elemental oxygen, which I would write as O. Anybody guessing? Anyone? Bueller? Anyone? 2. Elemental oxygen. That's how they exist in their natural state, normal state. You will find oxygen as O2. In fact, there's seven diatomic molecules that you will find in their natural state. Look on this periodic table. Can you find the number 7? Yes, because 7 diatomics, well, they all start off with the number 7. And number 7 is nitrogen, which we just went over. So nitrogen, N2, is one of the elements that are molecules, because there's 2 nitrogens. And then look, it makes the number 7. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. But how many of you are going, Norton, that makes 6. I thought you said there was 7. Yeah, there is 7. You can't forget the geek in the corner. So for all of these, they are diatomic, they are molecules, they are elemental molecules. Where am I? There we are, elemental molecules, because they're made up of exactly the same type of atoms. Okay, so again, back to the big 7. You don't really need to write this part down, just thought you'd want to know. Hydrogen, responsible for the big catastrophe of the Hindenburg. Yeah, that's it, made up of 2 little balls, exactly the same element, elemental hydrogen. And then we have elemental nitrogen, which is a lot of fun to play with, but I don't happen to have any. And then we have elemental oxygen, which is fun to breathe. And then we have elemental fluorine, which would not be good to breathe at all. Nope, not good. But these are all elements, even though they're made up of more than one atom, fused together, bonded together, chemically combined together. Okay, then we happen to have chlorine gas. Yeah, you wouldn't want to breathe this guy. Very dangerous, very kill you dead. Don't want to do it. Nope, so guess what? I don't happen to have any chlorine gas on hand. And then we have some bromine gas. It too can kill you. This is elemental bromine, made up of 2 different atoms. No, I lied. 2 of the, same atoms. That's why it's an element, even though they're bonded together. And last, the pretty one, iodine. Wonderful, beautiful purple color. And no, I don't have any of that either. You do not need to memorize the big 7, but you should know where they are and how to find them. And, memorizing might be helpful, but we'll see what happens with those. Something else that is an element that you might not think of an element is this guy. Now, please notice that each one of these balls are exactly the same. In fact, all of these balls are carbon balls. This stick right here is what we refer to as a bond. Sometimes you see models where the balls are all stuck together like this. This is called a space-filling molecule. Space-filling. And in the space-filling molecule, we don't actually show the bonds. We just puff up the atoms so that they're so big they stick together. This model that you're looking at here, this is called the ball and stick model. And in the ball and stick model, we use sticks as bonds, represented bonds, holding the atoms together as bonds. Okay, so atoms don't look like balls and bonds aren't sticks, but hey, they make for good pictures and they make sense to us visually, so we run with it. Can you guess? You know what this is. I know you know what this is. Even if you don't know what this is, you know what this is. Okay, you've heard enough of that? Actually, that's what a diamond looks like. That is the molecular or in tetrahedral structure of a diamond. And it's an element because it's made only of, you guessed it, carbon atoms. And now this one, oh look, is that an element? Well, yeah, because it's only made up of carbon atoms. And most of you should be using one of these when taking notes. It's, oops, the pictures are all backwards. But anyway, it's carbon. No, yeah, it's carbon. It's graphite. I threw myself off a little bit. Yeah, it's graphite. This is what graphite looks like. And look, just the different arrangement in the carbon balls. Graphite, diamond. Whoa, yeah. Anyway, they're both elements because they're only made up of one type of atom. This one's really cool. It's called a Buckminster fullerene, aka buckyballs, because they resemble the geometric shape of an architect who liked to use these, whose last name was Buckminster Fullerene. These were discovered, or actually first made, in 1985. Anyway, this molecule does those things you can read on your own. It's pretty cool stuff. If you Google buckyballs, you can see some really cool formations of this soccer ball looking object. It's an element. Why is it an element? Oh yeah, because it's only made up of one type of ball, carbon. Only carbons. I think there's 60 of them. 60 carbon atoms. C60 is how I would write that. C60. Only 60 carbon atoms all hooked up together and an element. Compounds are different from elements because they happen to have different types of atoms that are bonded together. That is the key word. You have to have different types of atoms bonded together. Different. Very important that they're different. Different. Carbon dioxide. Here is a space-filling model where we didn't actually show the bonds as sticks, so I drew them in. But look, we have carbon as yellow and oxygen as blue, and they're all bonded together. So is this an element or is it a compound? It's a compound. Of course it's a compound. Because, yeah, it's on the slide that says compound. And it's made up of different atoms, or in this case, different balls, bonded together. Oh, here we have water. You can always recognize water because it kind of looks like Mickey Mouse. Yeah, this is water. And in this particular water molecule, it's another space-filling model. And on a space-filling model, of course, I'm not going to show the bonds on a space-filling model, but I'll go ahead and draw them in for you because I am just that nice. There's a bond. There's a bond. This would be oxygen. These two are the hydrogens giving us the H2O, and it's a compound because different types of atoms. This thing is interesting. Is it an element or is it a compound? Yeah, Norton, it's a compound. You got it on that slide. Yeah, it is. It is a compound, and you'll notice it is a compound because it's made up of 3 different types of atoms. Now, here's an extra credit point for you. As an extra credit point, on your notes, I would very, very much like for you to write down how many of each different type of atoms there are. So, in other words, I'm asking you how many white balls, how many blue balls, don't laugh, and how many black balls are pictured in this compound. Now, there are 3 main states of matter. This should all be a review from middle school, but hey, middle school was so long ago. We'll just try it again. So we have solids. Solids have a definite shape and a definite volume. Well, these are all pictures of geometric solids that at some point along the way you should have to do some funky calculations with those. And all of the atoms are moving. They vibrate. Remember the rule, if I write it down, you need to write it down. The atoms in a solid, they really are moving. They're like vibrating in this fixed position. That's why it's got these little movie lines to it. And there's another picture. See how they're vibrating? They're kind of moving in place. That's what a solid looks like. Now, a liquid is a little different. The words that you want to fill in here for liquid is that it does not have a definite shape. And actually, you should write it down. It takes the shape of the container. That's a good thing to write down. Container. Yeah. Did I spell that correctly? Container? Okay, I'm going to run with it. Anyway, it takes that shape, but it has a definite volume. You know, can I get a 12-ounce soda pop? See, 12 ounces, definite volume. The atoms in this guy are also moving, but they're moving faster. Typically, they're moving faster. So the atoms in a solid are moving slower than the atoms in a liquid, provided it's the same substance. It's got to be the same substance. You got to compare apples with apples. You can't do apples and oranges. It's got to be apples and apples. So they make sure that they are the same substance, and then of course, yeah, the liquid's moving faster. And look, there's more distance between the molecules. There's more distance than there was in a solid. They're a little more spread out. I like to think of them as sort of like behaving like bees in a beehive where they're all like moving and grooving on top of each other. They're not in those fixed positions like you saw in a solid. Okay, now a gas, on the other hand, A gas has no definite shape and no definite volume. Gases are so cool because they're totally compressible. I'll get to that in a minute. These are classic gases. Helium, neon, argon, krypton, and xenon. These are what we call the noble gases. You should probably know that one, but yeah, noble gases. But that's okay. Noble gases. But what you really need to know is this. Gases, if you're using the same substance, because you can only compare apples to apples, you can't do apples and oranges, so it's the same substance, they move faster. As you go from a solid to a liquid to a gas, these suckers, these little balls, move a lot faster. That's what these zoomy lines mean. And because look at how much space there is. There's totally this huge amount of space, so large space. Between the molecules. There's a lot of space between the atoms or molecules, it doesn't matter, or compounds. But because there's a large amount of space between them, it is what we call compressible. You can squeeze a gas. And because it's compressible and you can squeeze it, in fact, you could squeeze it and squeeze it and squeeze it, you could actually get a gas to go back to a liquid just by squeezing it. Whoa, I know, right? Cool. Okay, well, that's it for today's video. You have some homework problems to do in class, collaboratively, etc., etc. And up next, I'm going to talk about the exciting physical properties of matter. And we've got a lab coming at you soon in your local high school.